Okay, so here, let's say, we want to find out R digit strings. So we want to find out R digit strings that is made of, so we call it the alphabet. So we can choose only 0, 1, 2, 3 in each digit. Is that okay? Okay. And then we want to find out number of ways on the number of R digit strings to get a string with, okay, so these are the criteria. At least 1, 1. Okay, we have at least 1, 1. At least 1, 2. And at least 1, 3. So how many ways to get a string that has this property? At least 1, 1. At least 1, 2, at least 1, 3. Okay. So it is a counting problem. And then we hope to get a generating function that works for all the possible R's. So R is equal to 1, I want to get a value. R is equal to 2, I got a value. R is equal to 3, I got a value. Something like this. I want to get something like this. And so you can think of this as what? The problem of I can choose zeros. I can choose ones. I can choose twos. I can choose three. And then after choosing 1, 2, 3, I can permute them and then get the permutation. And then out of all the different permutations, I want to focus on those that has exactly R objects selected. And then I want to get how many of them fits this criteria. Okay. So let me tell you how we can solve this. So we can imagine there are 4 types of objects. Type 0, type 1, type 2, and type 3. So there are 4 types of objects. And then we are going to create an EGF for each type. So let's do EGF for 0. So EGF for 0, it means that how many ways I can choose 0, 0. How many ways I can choose 1, 0, how many ways I can choose 2, 0, and so on and so forth. Okay, in all the cases. So just for 0, we have infinite supplies of zeros. How many ways? So previously we have only 5 dashes, right? So there's 1 way to choose nothing, 1 way to choose 1 dash, 1 way to choose 2 dashes, 1 way to choose 3 dashes, up to 1 way to choose 5 dashes, and that's it. But then for this 0, we have 1 way to choose 0, 1 way to choose 1, 1 way to choose 2, and so on and so forth. So what would that be? That would be 1 everywhere, right? Is that okay? So this is going to be the so-called EGF for 0. So EGF for 0 is going to be, what is it? E to the power x. Am I correct? Good. Okay. And then we will have EGF for 1. So what is EGF for 1? EGF for 1 means that how many ways to choose 0 ones that fits our requirement? No. we cannot choose 0, 1 because we need to have at least 1, 1. Okay, so there are 0 ways to choose 0, 1. How many ways to choose 1, 1? One way, right? Okay, can we simplify this? What is it? Very good. So e to the power x minus 1. Is that okay? Good. And then this is going to be equal to EGF for 2. And then this is going to be equal to EGF for 3. Is that okay? Let's consider the effect of multiplying them together. So what does that mean? Okay. So if we multiply them together, so this is, we have EGF 0 times EGF for this one, and then EGF for this 2, and then EGF for this 3. So this multiplying together, if everything working out so fine, no, sorry. This is x, and this is 3. Thank you. Okay, if everything works, then this will be a EGF to be using 0, 1, 2, 3 at any position. Is that okay? Okay. And then, so we have this one. This is going to be e to the power x times e to the power x minus 1 to the power 3. Is that okay? Okay, so let's expand this. So this is going to be e to the power x. This one to the power 3. So this is going to be e to the power 3x minus 3e to the power 2x. Am I correct? Plus 3 times e to the power x minus 1. Am I correct? Okay, and then this is equal to e to the power 4x minus 3 times e to the power 3x plus 3 times e to the power 2x minus e to the power x. Is that okay? Okay. And then answer. So what is the answer that we are? So the desired answer. Will be equal to, so we want to find out how many ways are there to permute, to get an R-digit string. So what do we want? We want to get the coefficient of this one to the x to the power r term of this one, multiply with r factorial. This is what we want. Is that okay? So let's give it a symbol. So let's call it e of x, okay? So we want to get, so the desired answer will be equal to, we have r factorial multiplied with the coefficient of x to the power r in this e of x. So if we can get this, if we can get the coefficient of x to the power r here, then done. Is that okay? Is that okay? So this is equal to r factorial multiplied with something. Okay. So what is the coefficient of x to the power r here? How does e to the power 4x looks like? How does e to the power 4x looks like? We need to be familiar with this one. So let's write down e to the power x again, and then we will see what is e to the power 4x. Okay, let's write down e to the power x again. So e to the power x is equal to 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus dot dot dot. Is that okay? So this is equal to what? So you can write it down as summation of 1 over I factorial x to the power I. I is equal to 0 up to infinity. Is that okay? Okay, now we want to get e to the power 4x. So we put 4x here. So we put 4x here. And then we want to get the coefficient of x to the power r term. So this will be 4 to the power r divided by r factorial. Is that okay? Does that make sense? So this is going to be 4 to the power r divided by r factorial. This is the x to the power r term here. Is that okay? Now, if you are okay with this, then this one, if you want to focus on x to the power r term, from this part, we get 3 to the power r divided by r factorial. And then we have a minus 3. So it is going to be minus 3 times 3 to the power r divided by r factorial. Is that okay? From this term, plus 3 times 2 to the power r divided by r factorial. Is that okay? And then the last term is minus 1 to the power r divided by r factorial. And this is the answer. So of course, when you see this, you have all the r factorial, you can cancel it. So the answer will be 4 to, okay, so the answer will be, let me copy it, and double check whether the answer is correct or not. So we get the answer. So the answer here is 4 to the power r minus 3 times 3 to the power r plus 3 times 2 to the power r minus 1. Is it? Double check, double check, double check. Okay, so let's do some checking. So what happens? Checking. So this is checking. R is equal to 1. What will happen? So how many one-digit string? So one-digit string that has at least 1, 1, at least 1, 2, at least 1, 3. 0. It should be 0. Okay. R is equal to 1. So this will get 4 to the power 1, 4, minus 3 times 3 to the power 1, 9, plus 3 times 2, 6, minus 1. Good. So this is equal to 0. Is that okay? Is that okay? Yeah, let's try another randomly. Let's try r is equal to 2. R is equal to 2, still 0, right? R is equal to 2, still, let's check. Okay. 4 to the power 2, 16, minus 3 times 3 to the power 2, which is 27, plus 3 times 2 to the power 2, which is 12, and then minus 1. So it is going to be 0. Is that okay? Okay. Let's try r is equal to 3. Okay, so this is done. So let's try r is equal to 3. So r is equal to 3, what should we get? How many string, r-digit string that has at least 1, 1, at least 1, 2, at least 1, 3? It must have exactly 1, 1, exactly 1, 2, exactly 1, 3, right? So there are 6 of them, permutation. So we should get 6. Okay, so let's try. R is equal to 3. 4 to the power 3, 64, right? Minus 3 times 3 to the power 3, so minus 81. Is that okay? Plus 3 times 2 to the power 3, plus 24, and then minus 1. Okay. Okay. Let's try. Okay. So this one plus this one is 88. This one and this one is 82. So the difference will be 6. Is that okay? So this works. Okay. 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 Yeah. Difficult to understand the general thing. But once you have this in mind, then go home and double check these two things together. And then you will find that it is very useful. Let's try one more example. This is an example that we have done before. Okay. So we have a different problem. This time, let's say with even number of zeros. Okay? So how many ways can we get a string with even number of zeros? Well, this problem, we have studied it before. We have studied this problem before. So if you still recall, altogether, there are going to be 4 to the power n strings. 4 to the power r strings from 0, 1, 2, 3, right? And then, so we don't have, so how many strings we don't have 0 and 1? So there are going to be 2 to the power, let's say, how many strings? Yeah, no 0 and 1. Yeah, sorry. So how many strings we don't have any 0, we don't have any 1 inside? There are going to be 2 to the power n of them, right? So these strings are made up of just 2 and 3s. Is that okay? And by definition, these strings are, so these strings are all having even number of zeros here. Is that okay? And then if you still recall, for the remaining string, exactly half of them will have even number of 0. So half of them has even, half of them has odd. So that's a long time ago, okay? That we have come up with a proof that shows that the answer for this one is equal to 2 to the power r plus 4 to the power r minus 2 to the power r divided by 2. Is that okay? So this is a long time ago that we have this one. And then at that time, the proof is not easy. We still need to find out, okay, there is a 1-1 correspondence between the string here and the string here, so that we know exactly half of them are even number of zeros, half of them are odd. Is that okay? So that's difficult. But now, let's try to use a generating function, the exponential generating function to help. Okay? So this one, we want to get the EGF for 0, EGF for 1, EGF for 2, and for 3, and then multiply them together. Okay, EGF for 1 is easy. There is no restriction about how many ones that we can choose, so it is e to the power x. Is that okay? Okay, so this is the same as EGF of 2, and this is also equal to EGF for 3. Is that okay? Now the problem here is, what is EGF for 0? For 0, there are restrictions. We can choose only even number of zeros. So how many ways can we choose 0 zeros? Now we have unlimited supply of 0, but we can only choose even number of zeros. How many ways can we choose 0 zeros? 1. How many ways can we choose 1 0? 0. We can't choose any, just 1 0, because we need even number of zeros. How many ways can we choose 2 zeros? 1. 3 zeros? 0. 4, 1. So it's 1 0, 1 0, 1 0. Is that okay? So if you sum them up, it is equal to I is equal to 0 up to infinity. We just have even terms. 1 over 2i factorial x to the power 2i. Is that okay? This is what we have. Well, this is a term that is difficult to manipulate. Difficult. If you just look at it, yeah. I multiply this one with this one. What do we have? Well, difficult, just difficult, right? But then there is something clever that we can do. Okay. This is going to be a useful technique. So let me write down. This is what we want to get. We want to get 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial x4 plus, this is the EGF 0 that we are looking at. What is EX? EX is equal to 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x4 plus dot dot dot. Is that okay? I want to make this go away. Is there a way to take this away? Just EX is not enough. We need something else. So if somehow I can get something like minus 1 over 1 factorial x minus 1 over 3 factorial x, that would be great, right? Well, this may not be easy, but there is something that we can use. E to the power minus x. This is a super useful one. What is e to the power minus x? It's going to be 1, and then minus, and then plus, and then minus, and then plus, and then minus. Is that okay? So what is it? You have EX is equal to this one. You have E minus X is equal to this one. What is it? So it is the average of these two, right? You add them up divided by 2. So this is equal to EX plus E to the power minus X divided by 2. Is that okay? Is that okay? Good. Okay. And then what remains is just routine thing. Let's work it out together. So now we get the EGF for X. Okay. So the EGF for X. So we can replace this nicely by e to the power x plus e to the power minus x divided by 2. Is that okay? Just as a sidetrack, so here we can get even terms. So suppose that I want to get odd number of zeros, but not even number of zeros. Then what should I do? You cancel the other parts, right? So you should look at something like e to the power x minus e to the power minus x. And then you divide it by 2. This should give you odd. And a strange question. So can we get something like, I just want a multiple of 3? Well, go home and think, okay, this is not totally impossible. This may be done. But it's not just like x and minus x. You need to find out something that you can cancel it like a 3-way cancellation. So this cancels with these two, this cancels with these two, something like this. So the average of them will give you what we have. Okay, but let's get back to the same problem. And let's get back to this original problem and see if we can use EGF to get the same answer. Okay. Okay, so let's use this side. So now we can have the EGF. So this is the final thing that we have, that we can use 0, 1, 2, 3 to permute, to arrange. This will be equal to, so you have EX, EX, EX multiplied with this one, right? So it is like 1/2 of e to the power 4x plus 1/2 of e to the power 2x. Is that okay? Okay. And then we are interested in what? We want to get the coefficient of x to the power r here. And then you want to multiply this with r factorial. So this is what we want. So this is the answer. The answer is equal to r factorial. And then this is equal to what? So it is equal to, so we have r factorial here. What is the coefficient of x to the power r here? So it is going to be 4 to the power, so I have a 1 over 2 here. So 1 over 2 times 4 to the power r divided by r factorial. Is that okay? And then for this one, this is 1 over 2 times 2 to the power r divided by r factorial. Is that okay? Everyone has R factorial. So it is equal to, let me use the blue one. So after we get a lot of cancellation, this will get 4 to the power r divided by 2 plus 2 to the power r divided by 2. Well, not the same, right? Well, the same. This is equal to 4 to the power r plus 2 to the power r divided by 2. Is that okay? Yeah. You get this is 2 times of this one. You do cancellation. That's it. Is that okay? Okay? So once you have this technique, you can solve. If let's say if I change the alphabet to 0, 1, 2, 3, 4, it is now not quaternary string. It's something like a 5-ary string. You have the same technique, except that you have this one, you have one more e to the power x to handle, and then you don't need to have this idea at mind, okay? Or maybe you can make the things more complicated. Maybe let's reserve this for the next class. So for instance, let's say today, so this is last year's homework. Let's say today I want to have an R-digit string that is made up of 0, 1, 2, 3, such that the number of zeros and the number of ones together is even. Together is even. So how many strings are there? Is that okay? So you understand my problem? So, okay, so let's study this problem next time. We have 2 different ways of doing this. One is we find out the exponential generating function for 0, 1 together, because now they are together. Multiply with the exponential generating function of 2, multiply with the exponential generating function of 3. So this is one way. We have also the other way. The other way is we use rule of sum. Okay, so I just mentioned the total number of zeros and ones together is even, right? It could be odd 1 plus odd 0, or even 1 plus even 0. Okay, so we solve this case by case, and for each case we can solve using the generating function approach. Let's examine this problem next time on Thursday. Okay. Thursday, right? Okay. So I hope you like this. So let's end the class now, and then see you on Thursday. Okay.